Welcome to this course about the spectral theorem for compact self-ajoint operators. Before we start, let me mention that this video and the complementary lecture notes are available at my webpage. I also assume that you followed previous courses in which the following notions were presented. First, self-ajoint operators on Hilbert spaces. In other words, Tx scalar y is x scalar ty for every x and y. Compact operators, that means operators that send the unit ball into a relatively compact set. In other words, the closure of the image of the unit ball is compact. And this can be characterized as an operator that sends a bounded sequence xn into a sequence txn, which has a subsequence that converges. Or can also be characterized as operators that send weakly convergent sequences into strongly convergent ones. So let us state the theorem. Start with a Hilbert space H, an operator from H to H, which will be compact and self-ajoint. Then there will exist an index set I, which is either finite or countable. A decomposition of H into mutually orthogonal spaces, such that H is the kernel of T plus direct sum of I in EI of EI. This last sum, I in I of EI, is the range of T. So that, like all self-adjoint operators, H is written as kT plus the range of T. Moreover, each AI has finite dimension. Next, there also exists a sequence lambda I, which is real, and the absolute value of the lambda i's are non-increasing. Further, if the set I is infinite, lambda I goes to 0. And then T can be written as sum of I in I, lambda I, pi I, where each pi I is the projection on the space EI. So if we take x in H, pi I of x is x if x is in EI, and 0 if x is in the supplementary, so that dx, if x is in EI, then we will have pi I x is x, pi j x is 0 if j is different from I, so tx is lambda I x. In other words, pi I is the projection on the eigenspace of T for the eigenvalue lambda I. Let me comment on this and rewrite this theorem in another form. We will choose an orthonormal basis of EI that we write EKI, where K ranges from 1 to Ni, the dimension of EI. In this case, pi I x, as we know from Hilbert space theory, is just sum from K equals 1 to Ni, x scalar EKI. And then the previous notation tells us that Tx is the sum of I in I, sum from K equals 1 to Ni, lambda I, x scalar EKI. What we have written here is that T is diagonalizable in an orthonormal basis of eigenvectors. While we have to be a little bit careful here, it's only an orthonormal basis of the range at this stage. To obtain an orthonormal basis of H, we must complete with a basis of the kernel. And this requires the kernel to be separable, and as the range of T is just the unions of the direct sum of the EI's, and this is a most countable sum of finite dimensional space, the range is automatically separable, so H has to be separable as well. Now, the problem is, if we want lambda k to be decreasing, we may not obtain an orthonormal basis of H. And write Tx is sum of k in n, lambda k, x scalar ek. We would still like to write this, but we will have to forget about the condition that the lambda k decrease. But as we will see now, we can still have lambda k going to 0. So what we will do to write T in the previous form is that we will write each basis and unite them and add a basis of the kernel. If the kernel has finite dimension, we put it at the beginning. If it has finite codimension, meaning the previous union of EKIs is finite, we put it at the end. Otherwise, well, we won't have the chance to do anything else than mixing the two bases, and then we lose the decreasing. In practice, this works as follows. We rewrite E11 to En11, the basis of E1, as E tilde 1 to E tilde N1. Then E12 to En12, the basis of E2. Well, we start with E tilde N1 plus 1 to E tilde N1 plus 2, and we go on like this. If the codimension of the kernel, meaning the dimension of the range in this case, is finite, this stops at some E tilde N, otherwise this gives an infinite sequence. We also take a basis of KRT, F1 to Fm, if M has finite dimension, otherwise it's Fk indexed with N. Then what do we do? We will unite both bases. If the codimension of T is finite, then we start with E tilde 1, E tilde N, and then add F1 and so on. And the corresponding eigenvalues will be lambda 1, lambda N, and then 0 and so on. And this is still decreasing to 0. If the dimension of the kernel is finite, then we start with the basis F1 to Fn, and then put E tilde 1 and so on. The problem is that the corresponding eigenvalues are 0, 0, 0, and then lambda 1, etc. And that's no longer decreasing, but still goes to 0. If both codimensions are infinite, we have to mix. It's E tilde 1, F1, E tilde 2, F2, and so on. The corresponding eigenvalues are lambda 1, 0, lambda 2, 0, and so on. They are no longer decreasing, but still go to 0. In other words, we can rewrite the spectral theorem as H is separable, infinite dimensional, Hilbert space. T goes from H to H, is compact and self-adjoint. Then there exists an orthonormal basis of H, and lambda k real, going to 0, such that Tx is the sum of lambda k x scalar ek, which is usually a much more convenient form. This can also be written in a matrix form, so that's a bit abusive because it's an infinite matrix, and there is a block, KRT, in the upper left corner, which may be infinite dimensional, so that these are two infinite blocks. So the block in KRT, the operator is 0, and then we have E1, E2, and so on with their bases, and in this block the operator is just diagonal. Lambda 1, etc. I would also like to stress that this theorem is well known for you when H is finite dimensional. It just says that a self-adjoint unit matrix is diagonalizable in an orthonormal basis. In other words, there exists a unitary operator U such that, and a diagonal operator D such that A is U, D, U star if A is equal to A star. Okay, thank you for your attention. There will be now a next video about an example. And recall that everything is available through my webpage.